Hi, I'm Callum Hodgkinson, a fourth year electronic and electrical engineering student at Harry Watt University. And today I'm going to talk you through lab 3 of high frequency circuit design. The aim of this lab was to create a quarter wavelength matching section. Well, matching circuit, yeah. This was to match two different sizes of resistors which symbolize antennas. One of them was 82 ohms and the other was 36 ohms. First thing you want to do is create your substrate. Then after that, you want to create your initial microstrip line, and you want that to be 50 ohms. We made ours 30 millimeters in length. The length is unimportant in this case. Then you want to add a 50 ohm terminal and a port as well. Then, because this one's 36 and this one's 82, the resistors, you want to make each, and the two branches are in parallel, you want to make each of them, each branch, 100 ohms. So that in parallel they equal 50 ohms and therefore they will match the resistor over here. You also have to make sure though that these transmission lines here and these ones here are of equal length. And also the corners have to be of equal length to them too, or else your layout will not come out perfectly and it can't be fabricated. So a good starting block is to start with your top line, and you want to make each of these transmission lines 45 degrees in length, so that in total they will equal quarter lambda. And because this is 36 ohms, a good starting block is to make each of these 64 ohms in impedance. And then you want to use the tuning factor to change it ever so slightly. But first of all, you have to create your bottom branch as well. So again, because this is 82, you want it to be 100 ohms, so you make each of these 18 ohms in length, and again 18 ohms impedance, and you want to make each of them 45 degrees in length. So after you've done that and you've tuned it, you should get, and you generate your S11, your reflection coefficient, you should get a graph of frequency against S11 that looks like this. As you can see, it's perfectly matched at 1.7 gigahertz with a magnitude of minus 59.879. Obviously that's pretty good, but a good benchmark to aim for is generally less than minus 30. So, after you've done that, you will generate your layout, which will look like this. So yeah, as you can see, these sections are matching because the corners and the transmission lines are all the same width, and the same down here. If they're not, then, as I said, the fabrication won't work. So once that was sent out to fabrication, I got it back and it looked like this. As you can see, it's created on FR4. So after that, you want to plug in your pocket VNA and you want to calibrate it. And since you're just doing reflection, you want to make sure this up here is on reflection, not transmission, or you'll get a lot of noise and not a good calibration. And since you're just doing reflection, you're doing a one-port calibration, so you only need open, short, and load. You don't need to bother with the through. So you do your measurement of your matching section, and when you generate the layout, you should get something like this. And as you can see, at 1.7 gigahertz, the magnitude of the S11 parameter is roughly minus 26 dB. As you can see, it's perfectly matched at about 1.725 gigahertz, but the frequency, matching frequency always shifts during fabrication, probably due to the fact that the simulation doesn't include this SMA connector. It can often shift the frequency of the design. As you can see though, because it is minus 26, it is an awful lot higher than the simulation results. Obviously the simulation results, as I said, don't take into account the SMA connector, and also it accounts for perfect resistors here and here, but obviously there will be tolerances in these resistors, and as with every fabrication process there are slight faults. Because of this, obviously the circuit won't be perfectly matched anymore impedance wise, but minus 26 is a very good result. So yeah, hope that helps, and yeah, that was lab 3 of high frequency circuit design.